So hello to everybody. We'll wait 1 or 2 minutes before starting this session of the Logical Universalist webinar. So welcome to everybody. We are starting now a new session of the Logical Universalist webinar. It is dedicated to the square of opposition. There will be the presentation of the book, the Exoteric Square of Opposition, which is related with the previous Congress on the square. So Ioannis Vandoulakis, with the chair of the session, and also the co-editor of the book with me and the co-organizer of this previous meeting, will say a few words about the meeting, the book, and we will also have a presentation by Danny Jaspers about the coming next event of the square, which will be in Leuven, Belgium, and then Roland Bolz will present his talk, which is a chapter of the book. So please, Ioannis, your floor is yours.
Yeah. Yes, I propose to start with Danny Jaspers and the future event to have a presentation, and then I will follow with the presentation of the book, and logically follows the presentation of a chapter of the book.
Very good.
Okay, so please, Mr. Jaspers.
Okay, I will share my screen. Is this visible for everybody?
Yes, for me, it's okay.
Okay, good. So this is the presentation on the 7th World Congress on the Square of Opposition in Leuven, to be held on September 9 to 13 this year. And as you all probably are aware of, it's a continuation of a whole series that started in 2007 in Montreux, and then had further installments in Corte, Beirut, the Vatican, Rapa Nui, and then Crete. First of all, with respect to our call for papers, as you will have noticed, due to the coronavirus, the event had to be postponed from September 2020 to September this year. The initially accepted abstracts were automatically approved for presentation this year, so they did not have to be resubmitted. But a contribution for the 22 edition is still possible. So the question is to send a one-page abstract before the 31st of May to our Leuven address. The topic of the conference is the historical and systematic aspects of the square of opposition. As you know, the history of the square of opposition traces back to the logical works of Aristotle, and throughout history, many authors have made use of the square itself and other related diagrams to illustrate their theorizing. Not just the history, but also the systematic aspects are part of what we will be doing. In contemporary research, the square has shown itself to be very valuable for a whole research community concerned with different types of logical reasoning, including philosophers, logicians, linguists, and so on. And the main topic sprouts a diversity of topics relating to the history of the square, going from Aristotle to recent extensions by Jacobi, Sesma, Blanchet, Soriol, and so on. A second range of topics is the applications of the square in proof theory, model theory, debates and politics, music and arts, and so on. And third, different variations of the squares, of the square in theories on quantification, elliptic squares, deontic squares, doxastic squares, modal squares, and so on. And finally, there are the extensions of the squares that have seen the light of day in the different square conferences that we've had, namely the extension to hexagons, octagons, and decagons, and also in different dimensions to cubes, polyhedra, and polysimplexes. Keynote speakers at the conference will be Janie Brisson, Oksana Cherkashina from Moscow University, Christoph Geudens from Leuven University, Spencer Johnston from Cambridge University, Fabien Chang from the Federal University of Goiás, and Atsushi Shimojima from the Doshisha University in Kyoto. Tutorials will include a tutorial by Wolfgang Lenzen from Osnabrück on Abelard's theory of opposition, a tutorial by Salou Achati from the University of Tunis on logical oppositions in Avicenna, and then a third tutorial, Leonardi database. Leonardi stands for the Leuven ontology for Aristotelian diagrams, which is a database, an online database. It will be on logical geometry. So the goal has been to collect as many concrete Aristotelian diagrams from the literature throughout the centuries and from different sources, which will provide or which will be made available for the whole research community online. Of course, there are the contributed talks where we are at the moment at some 62 of them. And then on Sunday, the 11th of September, towards the end of the day, we will first have a guided tour at 5 o'clock through Leuven, which will also include its famous library. After which we, after stretching our legs, we will then be ready for the conference dinner at 7 p.m. that night. Briefly, some practical matters. The registration is 200 euros for the regular registration fee before July 22. A reduced fee for students or people with low income, which is 100 euros, and that doubles on arrival. So for people who are latecomers. Finally, I also mentioned the sponsors, which are our own university, KU Leuven, the Research Foundation in Flanders, FWO, Spring and Nature, the Research Council in Brazil, and the Logica Universalis Association. And you can also find the link, of course, to the this Square edition on the General Square website. So I hope to see you all in Leuven, Belgium, for the 7th Congress on the Square of Opposition on September 9 through 13, 22. That was my presentation from Brussels. Back to you.
Thank you very much. Are there any questions, clarifying questions about the Congress, the abstract, the submission, deadlines, all these things?
I would like just to say that because maybe not everybody in the world know where is Leuven, but it's a town which is very close to Brussels, and especially to Brussels airport. So it's very easy to go from Brussels airport to Leuven. And maybe Danny will say a few more words about that, and also about accommodation. I think it's quite easy to have good accommodation in Leuven and so on. Well, put information on the website, but it's good maybe already to say a few words about that, Danny.
Yes, we will make available a list of places and of addresses that are good where people can find accommodation. So we're still setting that up, but that will certainly be made available on the site. And indeed, Leuven is easily accessible from Zaventem. It's actually equally as close from as the center of Brussels from Zaventem. It's very easy to reach.
How much time you go from the airport to Leuven? More or less?
I think it's half an hour at most.
By train, there are some direct trains.
There are direct trains, yeah.
From the airport, okay, very good.
Yes, from the airport, so there is a connection from the airport. And well, people who still want to submit can do so till the end of May, so they still have a few days to do that for the who still want to be added to the list or want to see whether they can still be accepted for the conference.
Okay, thank you very much. Then I will proceed with a presentation of the previous square and the books and journals that we printed with the works of the previous edition of the square. Just a minute to share my screen. So the 6th World Congress on the Square of Opposition was held in Crete, in Kolimbari, the premises of the Orthodox Academy of Crete in 2018. And their main organizer was the Logical Universalis Association. The host, the Orthodox Academy of Crete, was located on the western part of Crete, and the location was magnificent because there was a view of the sea until the Chania city. This is the environment of the Academy, Orthodox Academy. It is quite interesting environment. Now we have the new the arrivals, the first arrivals, and the opening. These photos are from the local press. They gave much publicity in the local press. There were long reports about the Congress. So we have here some photos. All these photos were published in the local press and in the websites of and blogs of journalists. So here are some presenters, some contributors, invited speakers, and here is one of the presenters today. And the outputs of this conference was first the handbook of abstracts. The second was a special issue of Logica Universalis journal with many papers. And a third is the forthcoming book, The Exoteric Square of Opposition. The contents of the book you can see here. We'll pass through quickly. There's an introductory part, a paper by Gianluigi Segalerba, by Salua Satie, by Sumanta Sharma, by Trzezinski, Valentin Pluder, Heinemann and Demi, Lemansky and Schank, Bolz, Béziot, and Schuller. And Mruzek Nasimievska and Marek Nasimievski, Kuvrekis, Stefanias and myself, Julio Stern, Regis Agot Pelissier, and Alessio Moretti. These will be the contents of the book. I will pass through quickly for some events we had during this conference. We had an excursion to Chania, to the old port of Chania, and to the old city of Chania. And we reached also a monastery of the 17th century, which is very peculiar monastery because although it is an unorthodox monastery, you can recognize this kind of symbol on the facade of the monastery. This is the triangle of contrariety. This can be explained because the founders of the monastery, the Zagaroli family, for this reason, it's called the Zagarolon monastery, were converters from Catholicism to Orthodoxy, and therefore they were bearers also of the Western culture, and for this reason, maybe we can recognize this sign in this architectural complex. This is not a usual, so to say, Orthodox monastery with this scheme. Here are some photos from inside. Then we went to the cemetery of Venizelos. Venizelos was a Greek leader from Crete. Here is a panoramic view during the dawn. And finally, we had a dinner at the Venetian port. and a Cretan evening at the Academy. So that was the event and the output, so to say, of this event. And now I would like to invite Roland Bolz for his presentation of a chapter of the book, The Exoteric Square of Opposition.
Thank you, Ioannis. It was nice to see those pictures, brought back some memories. I'm happy you didn't show any of the photos when we all danced the Sirtaki. Yeah, thanks again also to Jean-Yves for the invitation to present this. I'm going to talk you through the argument of my paper, and I'll show you a lot of diagrams and graphics, and I'm going to do it here. So I'm going to show you diagrams, but I would like to ask you to put Zoom on the so-called speaker view if you don't have that already. So you should be able to read these labels. Yeah. So in my Zoom, that's at the top right corner. You can switch between gallery view and speaker view. All right. So the title of my paper was Logical Diagrams, Visualization Criteria and Boolean Algebras. And I sort of make some connections there. So by logical diagrams, I mean the square and the hexagon and that whole family of diagrams. So yes. So in my paper, there are 3 themes. The first theme is to look at these diagrams as attempts to visualize something that is not spatial. Okay, logical structure is not spatial. The concept of the finite and the concept of the infinite, they are logically linked by way of negation, but their relation is not something that is in space. Yeah? It's an abstract relation. So if we create diagrams to visualize this information, we should treat it as an attempt to visualize. And so one of the first themes I develop in the paper is this visualization perspective. So I'll start with that too. I also set out to study a number of diagrams that perform really well, that are just great as very complete and elegant visualizations of certain logical or mathematical structures. And I'll talk about that too. But in the paper, I say, while the underlying structure, maybe you can look at it more as a combinatorial structure and look at some of the logic stuff as a special case of that. So that's the second point. And I also sort of comment on these series of polytopes that have these nice features. In the paper, I call them Boolean polytopes, but an alternative that I like a little better now would be rota polytopes as a homage to the combinatorics, the mathematician and the combinatorialist Giancarlo Rota. And a new theme that I might develop if I have enough time is I have a couple of observations about conceptual structure and what kind of terms we tend to lexicalize. So yeah, let's see if I get to that. So the central idea, again, starting with this idea of visualization, is that logical diagrams are attempts to visualize otherwise non-spatial structure. Yeah, that's of a mathematical or logical or conceptual kind. And I was sort of developing this idea that, well, if there are attempts to visualize something, then maybe we could start to lay out some success criteria for a nice visualization or an elegant visualization. I wasn't aware of anyone in the literature sort of addressing that topic, so I just sort of gave a sort of first sketch of how we could approach it. And for this, I sort of set up these four criteria, which you can read in a paper. But yeah, the basic idea is completeness. This has to do with the fact, well, if you're studying a little logical structure, and you sort of want, if you're going to create a diagram for it, you're going to want that to be complete, because any diagram by itself, any visualization, sort of suggests to a reader like, this is a complete representation. So we want to favor diagrams that are nicely complete from a mathematical or logical point of view. Correctness, you don't want to make any mistakes. Yeah, so this is more of an implementation issue, not so much a design issue. So in the paper, I refer to absence of distortion, the third criterion. And this, well, what I try to capture by this is that geometric shapes, when we see them presented to us, we try to look for meaning. So if there are certain salient features of a diagram, like, for example, if you prominently have a big triangle, we start to think like, yeah, those three things must make up some sort of trinity together. So the more you don't want your you don't want your diagram to have all kinds of salient geometric and visual features that don't have a meaning, because then they are overly suggestive. So that's really what I mean by this. And legibility refers to the fact that, well, we want human readers to use these diagrams as objects to think with. So they have to be legible. They can't be too busy. They, yeah, you have to be able to sort of still grasp them at a gestalt level. So you can improve the legibility sometimes. You can stretch that a little bit by adding a little explanation of how a diagram is to be read. And you can take away some of the possible distortion by writing a little legend or a guide to how to read this diagram next to a diagram. That's just a suggestion, but I haven't seen that yet. Now, I'm going to also talk about completeness in two senses. You can think of completeness of a diagram in a mathematical sense, or in a logical sense, or a combinatorial sense. So if all the possible inferences, all the possible labels, all the possible combinations are in the diagram, then it's mathematically complete. But that doesn't really mean that it's, maybe cognitively complete is a little less than mathematically complete, but it's constrained in different ways. And I also think that our diagrams should pay attention to this. And that's the final part of my talk, where I might just offer some remarks there. But yeah, this just sort of to set it up for. So let's look at some classical examples. On the left-hand side, you have a square of opposition. This is not the most famous square. It's this one is about the comparison of numbers according to their size. Yeah, and you can see in total 6 relations being laid out for you. A red line means that they are so-called contradictories. These two terms can both be true, can both be false, and the same across here. Now, the blue line means they can't both be true. However, they can both be false in this case. And a green line means they can both be true, but they can't both be false. And a black arrow means, well, if that's the case, then a fortiori, that's also the case, because it's strictly speaking a weaker thing to state. Yeah. So that's a square, and this is a hexagon that is a completion of this square. So I already mentioned that this is not an exhaustive set of options. Well, here you have the missing link, and there's another missing notion here. And now you really have some sort of completeness. So this is not just a completion, it's also, once you have this, you might say, well, is this really so nice as a diagram because there's some parts missing? Yeah, we prefer this one. That's at least my sort of reasoning with these diagrams. Has many beautiful visual features. So these red lines are the negations. I would like to emphasize this blue triangle here states at the finest level of distinctions. That states what all the three options are ultimately. And then these other three terms sort of, they're like a little bit more agnostic. Like if you don't know whether A lesser B or A equals B, then you can say A lesser equals B. So that's weaker. And that you get those notions alongside the finer grained distinctions of the blue triangle. Here's another famous example. Now I see some chat coming in. I'm just going to check if that's okay. I'm going to respond to your questions later. It's not going to be useful to pause. So, oh yeah, well, I'll answer that. So the diagram is spatial, the figure is spatial, but the relations between these terms is not spatial. It's linguistic or logical. There's no, this is not a map of a territory which is itself spatial. It's a visual representation of structure that is not spatial or geometric. So, okay, I'll continue. This is another sort of famous example where you have all of those terms laid out. So both of these examples that I gave are, and this has been established in the literature, they are sort of complete diagrams and from a design perspective, really successful diagrams for logical systems or conceptual systems up to a certain complexity. And once you go up one step, well, you can, once you go beyond that complexity, the diagrams can become more complicated. And then there's an analogous diagram that is also complete in the same way that this is complete for this complexity. And that's a three-dimensional diagram. And for now, I sort of just want to show it to you more as a geometrical shape, and we'll talk about the meaning later. And the labels, but here you have 14 vertices, and it's sort of, it's a three-dimensional shape. Obviously, you can sort of look at this as inscribed on a sphere. And well, let me show you. This is what it looks like if you make one from paper. You can sort of see these four faces. Sometimes you get 6, and you can think of it a little bit as a cube. Yeah, cube of these pyramids. So that's sort of what that is. So yeah, it has been established in the literature. I'm thinking of the work of Régis Pélissier, the thesis by Alessio Moretti, and also a series of papers by Laurence de May and Hans Messert. Has been established that this diagram is the next complete one for this level of complexity, in analogy to how this one is a nice and complete one in relation to that level of complexity. So yeah, we'll spend a lot of time with this one, so you'll understand it a little better towards the end. But yeah, when you, so I became fascinated in why these diagrams are so nice as visualizations of that underlying structure. And of course, well, neither of these two examples, well, these are both nice examples, but you wouldn't, like if you were to study the underlying mathematical structure, you wouldn't necessarily use those, here it is. You would necessarily use those as your canonical example because they're both quite specific to these, here the quantifier terminology and here this mathematical order terminology. And so what you end up doing, if you understand it better, is you end up labeling, finding a sort of canonical labeling of the corners. And this is the canonical labeling I use when I'm just thinking about how the geometrical object reflects mathematical and logical structure. So I label the edges with the subsets of a 3-element set. Yeah. So this is pretty much a Boolean algebra of a 3-element set that you can see here. And I really look at it as this. And I think throughout the talk, it will become clear why I favor that perspective, at least when I'm studying the sort of structural relation between, again, the geometric shape or figure and the non-spatial logical structure. And by the way, this is equivalent to something that Hans Messert and Lawrence de May have come up with that's called so-called bit string notation. And that's also quite similar. However, I think I've added a couple of small insights, and I just have my own notation that I favor. So yeah, now you should sort of look at this as a diagram of the subsets of a 3-element set. And if we now go up one level of complexity, diagram I already showed you, you can see that something analogous is happening. We now have all the subsets of a 4-element set, and they all just sort of neatly spread out on this polytope. The edges are labeled, yeah? So if you look at blue dots here are the 1-element subsets. And the green dots, the green vertices here are the 3-element subsets. And then there are 6 more on the top of these pyramids, there are 6 more 2-element subsets. Yeah. So it's really a visualization of a Boolean algebra of a 4-element set. Yeah, the Boolean algebra and the power set of that, of a 4-element set. And other aspects of the Boolean algebra are also in this geometrical figure in a way. Well, for example, in a Boolean algebra, you have complementation. So if you take any element, then you will have a complement. So for example, this element here, the subset that has B and C, well, there will be a complement of that, and that's here. So that's a subset that has A and D. And the cool thing in this shape is that that will always be at the exact opposite of the polytope. Yeah. So look, like here, this green one stands for ABC. And then D is at the other side of the cube. I don't know if you can see that that's spatially on the other side of the thing, but you can sort of, if you look at this one, you can imagine how, for example, that one aligns with the same thing on the bottom as a line symmetry. So that's a canonical representation. And then in the paper, I really ask, well, why are these geometric representations so extremely nice in relation to that logical structure? And in my case, I've started to look at it more as combinatorial structure. And I basically discovered the following pattern. So there's an extremely tight analogy between 3 fundamental combinatorial structures and aspects of these geometric items, geometric objects. And this list sort of states them. So again, on this side, this is a non-spatial combinatorial structure. Subsets, power set lattice is one thing, and then that sort of neatly maps onto the arrangement of the vertices of these particular geometric shapes. Here we have the partition lattice, and I'll explain that a little bit for those who are unfamiliar. And that actually maps in an amazingly precise way onto the symmetries of the diagram. Finally, the permutations map onto here. And actually, after publishing the paper, I discovered that the list goes on, but yeah, that would be too much to explain today. So I'm going to take you through all three of these, and I will do it with the help of some diagrams and some things that I drew for you, just to establish that analogy. So that establishes the combinatorial background of how these figures can be understood. So the first concept is the idea of a, need to keep some of these, I need to use them later. The first idea is the subset lattice. And this is known to all logicians and mathematicians who've taken set theory. It's just such an elementary sort of set theoretic notion. So if you take a 3-element set, you have an inclusion lattice on the subsets. And this sort of shows you that. And well, this is a nice diagram, but in the hexagon, it ends up looking like this. Yeah? So that's sort of wrapped, it's on a circle. And yeah, I know, what can I say? It's just very regular. So yeah, in this one, you have the same idea, but there's more in the picture. Yeah, so you might not really notice that unless you looked at the figure that's one step more complicated, the Tetrakis hexahedron. Yeah, by the way, I didn't say that. So this figure, geometrically speaking, is called a Tetrakis hexahedron, which means tetra is 4, hexa is 6. So 4 times 6 is it has 24 faces. Yeah, Tetrakis hexahedron. So that comes up in the paper a lot. So back to Boolean algebras on subsets. So this one I realized in the last minute that I didn't have, so I sketched it just with a pen. So if you have a 4-element set, that's just slightly richer, because you have the layer with 1-element subsets, 2-element subsets, and 3-element subsets, and those relations get a little bit more finicky. I didn't really succeed at making a very beautiful drawing of that. But if you look at this one, actually it's extremely geometrical, and you have all the arrows that were in my previous drawing, they're in here. So actually exactly all the edges of this polytope are the inclusions. I have to mention that the universal set and the empty set have been left out, but all the other ones, they are here, and they make up basically the ribs of this figure. Yeah, so that's the Boolean algebra on the subsets. So that's 1 out of 3 geometric analogies. The second one is the let me show you this for a sec. So we finished subsets, and I'll now show you that the partitions of a 3-element and a 4-element set have geometric counterparts in terms of the symmetries. Now, this will be a little harder to wrap your head around if you're unfamiliar with all of this, but I'll do my best and use some diagrams. I hope I'm not over-explaining this, but here it goes. So if you think of a 3-element set, there's exactly 5 ways to partition that into a number of non-overlapping families. So for example, you could take 3 families and put 1 element into each, and then they've all been separated, partitioned into a different subset. You can put 2 of the elements together in one family and then 1 separate, and that can be done in 3 different ways. And then you can just lump them all together into 1 partition. So in case that's not super intuitive, you might consider this diagram, which I drew yesterday. We can identify all those into 1 family. Then we could also take those 2 elements. So here that would be A and B together and C separate. You can have B and C in 1 family and then A separate, etc. Or you could all have them all separate. And the idea is, these three partitions in the middle will show up in here as the red lines. And these red lines are sort of geometrically specific because they are the symmetries, the line symmetries of this hexagon. So each line symmetry of the figure corresponds to one of those partitions into two binary partitions. So AB and then C, that's a binary partition, etc. So yeah, you might find maybe that framing is a little overly technical, and I would agree with you at this point. But where it really comes from is if you look at the for the three-dimensional case, then this pattern becomes more obvious, and then retrospectively this makes a lot of sense. So yeah, I'm gonna if you remember this diagram, so that was the partitions of a three-element set, and here are the partitions of a four-element set. I'm gonna need to come up a little bit, I think, to be able to show that to you. Yeah. So if you take a four-element set, you can lump them all together into one great family, no partition, just one family, or you can take them into two families. So that could be three elements lumped together and then one separate. That's these four. Or you could do a binary partition into two families, but they are 2 by 2, is these three. So you have these 7 binary partitions, and then you have here 6 ternary partitions. So that's partitions into 3 families. And in this means those two get lumped together, but these two have their own, they're separate in separate families. So 3 families, 1 with 2. And that's the same here. Or finally, you can do them all separately. And now, well, I'm just going to show you a little fragment of that. So yeah, so what I'm going to explain next is these lines, because there's now a sort of order structure on there. And we'll be able to find all of this mathematical structure geometrically in the figure. And of course, I'm going to point out that sort of anecdotally, but yeah, just to show you what that line stands for. So this is a binary partition. It partitions a 4-element set into that set and then this 1-element set. And this is a ternary partition. It partitions a 4-element set into 3 sets, lumping these 2 together, and then that one separately and that one. So this is a finer partition because it makes more distinctions, and that's a coarser partition. But well, this is coarse because it only distinguishes between that element and that element, that element and that element, that element and that element. But it doesn't make distinctions inside this larger set. So it makes 3 distinctions in total. This makes a few more distinctions, but the crucial point is that this partition makes at least also those distinctions that this partition makes, because it makes a distinction between that element and that one, and that one and that one, and that one and that one. So all the distinctions that this partition can make, this one also makes. So we call that a refinement of a partition. And in this case, it doesn't apply. So I've crossed that out because this partition makes a distinction between that element and that element. And this partition does not make that distinction. So this is a finer partition, but it's not a refinement of that one. So I hope you could sort of follow that on the hand of this with this small example. And so all of these lines here are refinement relations. So there's a neat sort of order structure on these. Yeah. And the cool thing about the Tetrakis hexahedron diagram, and geometrically speaking, is that all of this has a neat geometric interpretation in the diagram. And I hope to show you that by way of an example now. So recall, we have, these are all binary partitions. They separate the 4-element set into 2 parts. Yeah, these are ternary partitions. They're all 2 + 1 + 1. They separate it into 3 parts. So I'm first going to show you where to find binary partitions, by way of this example. A binary partition exists between A, separated off from BCD lumped together. And in this case, and I already pointed this out earlier, let me come in a little bit to get you. Yeah. So in this case, you have the point A is here, and the point for BCD is here. So those are at opposite sides of the shape. It's a line symmetry through the center. And this geometrical shape, it has just a geometrical feature that there are exactly 7 line symmetries that it has, or you could look at them as rotational symmetries. And those stand for all 7 of these binary partitions. So for example, you could go from AC to BD. That's again a binary partition. And that will be on the other side of the figure. So again, yeah, so there's a nice analogy between this whole layer of the partition lattice and the symmetries of the polytope. And however, these ternary partitions also have a counterpart. And so in this example, let's get this out of the way for a second. And come in a little bit. So in this case, this is a ternary partition, a partition into 3 distinct families. And in this figure, you find the point A here, point D here, and then the point for BC here. And those 3 figures determine a plane. And it's not just any plane, it's a plane that cuts this figure into 2 symmetric halves. So they're sort of plane symmetries of the figure. And well, we have 6 ternary partitions, but this figure also has exactly 6 plane symmetries. So that also has a sort of representation. And what's even a little bit more funky here is that I told you about the refinement relation. So maybe if you remember, or if you don't remember, it doesn't matter, but this is a finer partition because it partitions the 4-element set into 3 families. This is a coarser partition, 2 subsets, but that is a refinement of this one. And what you will find here from a geometric point of view is that that line lies on this plane. And that is true if and only if the one is a refinement of the other. So I hope I didn't over or under explain that part, but I will move on to the last part of my analogy here. So I told you about this part of the analogy and then this part of the analogy, how that sort of maps onto a geometric feature. And then finally, permutations map onto facets. So a permutation of a 3-element set is basically, you got to look at these elements as characters, and you got to compose a string that uses each character exactly once. So that is an enumeration problem that has exactly 6 solutions. And so C, A, B. But what I'm showing in this diagram is that you can look at these as paths through the Boolean algebra of the subset. So these are not completely disconnected combinatorial concepts. And this has a really nice counterpart in our diagram here. Let me show you. So here I've just added that point in the middle to clarify things. So there's exactly 6 little triangles here. And all of these 6 stand for a permutation, because you can look at this triangle basically as going out or starting at A, then going to AB. So that means adding the character B, and then finally back to the middle C. So this is the permutation ABC. Now this would start at B and then add A and then C. This starts at B, so that becomes BCA, CBA, CAB, and ACB. And then you have this nice feature that, for example, ABC is the opposite of the inverse permutation from CBA. That always ends up at the other side of the diagram. So again, some really nice geometrical features here that align with some really fundamental combinatorial stuff. And it continues here. So in this case, you can start to look at these. So this figure has exactly 24 faces. And as it happens to be, there are 24 permutations of a 4-element set. And you can sort of look at these faces and you can see, well, each face chooses a 1-element set, a 2-element set, and a 3-element set. And that's enough to determine exactly one permutation, because you read it this way. Well, you start with the 1-element set, that's your first digit. Then you go to your 2-element set, so there's adds a digit, 3-element set, adds a digit, and the last digit, you can think of it as being inside or whatever you prefer, but that sort of, once you've chosen the first 3, then the last one is automatic. So again, all these 24 faces stand for permutations of a 4-element set, or a string of 4 symbols. And again, you have all this nice behavior where the inverse permutation is on the other side. Adjacent faces are permutations where 2 characters have been swapped. And it sort of really behaves quite nicely against the background of the types of operations you might expect on permutations. Yeah, so that was sort of this part. And I gotta make a couple of remarks to tie this together in relation to how I started my presentation. I've shown that there is this analogy for these diagrams, for these geometric objects. And that explains why they strike us as extremely complete and rich sort of geometric shapes to look at when we are studying that structure. I do sort of suggest that looking at it from a combinatorial perspective is a bit more transparent if you want to work out that analogy than if we look at something like this where we started. Yeah, because it's a little less transparent. Yeah. Yeah. So in terms, if your goal is to aim for completeness in a strictly mathematical or logical sense, then at least these 2 diagrams score very well, because they have many geometrical features that have readings that you could translate to logical structure, or you could read it directly, as I did, as combinatorial structure. So yeah, I'm sort of looking at the clock. I have 37 minutes. So I'm just going to dive into this last part, and I'll probably take about 5 minutes. So yeah. So yeah, we started here. And now I'm going to talk a little bit about cognitive completeness, or how we conceive of some of these domains. So one thing here is I pointed out the importance of that blue triangle in the middle. Yeah. And because the blue triangle basically says if you use the finest grain distinctions, then those are your 3 options ultimately. Yeah, this conceptual system doesn't make any finer distinctions with this vocabulary, at least. So really, you gotta maybe focus on something like this for a second, and then And I started thinking, well, do I really like that triangle, or what does it really convey to me? And I sort of feel like from a visual communications perspective, from a design perspective, a triangle like this suggests that they are completely equal and unordered. So the relation between these two, is as the relation between these and between these. And indeed, that's what the blue lines have been made to mean. However, when I reflect on how I conceive of this domain, it's a little bit more like this. So if you think of holding B steady, let's have B fixed. Let's say it's 500. Then all the cases where A is smaller feel like they are more on the left-hand side. Then this is right in the middle. And then when A becomes bigger, it's there. So perhaps that sort of linear structure here is also important for how we understand that. And of course, in this diagram, that is at least not emphasized visually. Yeah. Here's another example. So I've just used the blue triangle, all A or B, no A or B, some A or B. This is a bit sloppy. Some people don't necessarily agree with this, but you get the idea. And my point here is the way I conceive of this is there are two extremes and then a whole range in the middle. And if I'm going to represent this conceptual structure, I kind of want to be reminded of that. I don't want to de-emphasize that as much. And here's another example that's a little more complex. So if we talk about the cardinality of sets, the conceptual apparatus has been created, from Cantor onwards. And these are just the finest distinctions. Of course, there's more to the right here, but I'm sort of focusing on this part. A set can be empty, could be finite non-empty, could be countably infinite, LF0 or larger. So these are some really fine distinctions. But this is a base 4 system. So you have 4 distinct domains that you are distinguishing between. So if you want to map that out in a logically complete way, you're going to need a diagram of this complexity, and you have to label everything accordingly. So you have to do these, the A, B, and C, and D would have to be labeled with these basic terms, and then the rest sort of gets filled in on top of that. And I sort of ask myself, where is that really helpful, and how do I think of it? And then I sort of came up with this one. So do I really need all 14 of these concepts, or do we focus on some of them more? And my hypothesis is that typically a lot of these domains that we use in diagrams are linearly ordered if you go to the finest grained distinctions. And then the lexicalized concepts, those are the ones that are shortest, and tend to have there's some constraints on those. It's really only the ones that split the domain into 2 parts. So for example, countable is downwards from here, but all the way down. Non-empty is upwards from here, but all the way. So these sort of contradictory pairs, they have this feature of stratifying the linear domain into 2 complete regions. So I think that's sort of just, those are just some observations as to how we might start to think about some cognitive constraints on what is really important and interesting. So you could do a diagram in this style and label it with all the different distinctions, and it would be logically and combinatorially complete. But it might not even be a helpful teaching tool, or it might not be something that would be a lot of fun to look at when you're trying to understand this. And something a little more schematic and less geometric like this, which picks out the salient distinctions, again, in relation to this linear domain, might be equally useful. Yeah, so to sort of come back to where I started, all my papers here are completely in a big pile. The idea, well, I sort of talked about visualization from 2 points of view. Like if we are really interested in these really complete, mathematically complete systems, then you're going to end up with Boolean completeness, and it has a lot of links to combinatorics. So that was one point. But I'm saying here that it's okay to be selective, but you have to make a selection based on some sort of idea of what cognitively constrains how we actually conceive of this domain. And of course, going from a linear order here is an immediately obvious idea. So if you are going for, yes, here we are. If you are going for cognitive completeness, then you might end up with diagrams that are not very geometrical, but maybe something like the one I drew here. And that was just a case study. And if you go with mathematical completeness, and then you might end up studying things like this one or the hexagon. So let me switch back. Yeah, so thank you very much for listening. That was my presentation. I hope it didn't go over by all too much. And I look forward to a lively discussion.
Okay, Oksana Cherkasova has a question. Please. Oksana?
Boom.
Oksana?
No, it's me. Okay.
Oksana Cherkasova has raised her hand, but she's not here, possibly. David,
Yes,
microphone.
hello, I'm glad to see you. I was very interested to listen.
Me.
Okay, to this talk. Yes,
Yes.
do you hear
You
me?
have a question?
Yes, yes.
Yes, please.
So I would like to show you something, if I may.
Yes.
So do you see this?
Yes.
This is my presentation for the future square accepted 2 years ago. And as you can see, it's very close to what you are doing. So I'm using this for a different goal than you do. This is a 5-element set, and each element is in this lantern has a methodological meaning, representing possible relations between 2 non-empty sets. In this way, you can take 4 coordinated vertices and create an analog of the square of opposition, or some either the square itself or a similar figure with slightly different features. So this has a methodological meaning. And I was wondering how our research could be combined, how your research of the features of this, so to speak, lantern could be used with the language that I'm using, because this is a special language that partly Professor Markin created, partly I did. So I was wondering how your methodology could be combined with the language that I'm using. So I would be very interested to listen to your future talks and to read your paper, if I may.
Thank you.
Thank
Yeah,
you.
I'm not muted. Thanks for your remark. I would have to study it a little bit to give a good answer. I'd be curious to receive your correspondence or to read about it. Yeah, that's really what I can say. But I do think that looking at combinatorial structures in relation to the square is that, yeah, I mean, that's definitely something that I've done, and I'm really sure that there are more links. But yeah, just at a glance, there's not a whole lot I can really say. Yeah, hope that's not all too disappointing.
So if you don't mind, I would like to exchange our papers to look at yours and to send you mine.
Okay, I'm going to type my email address to you.
Thank you.
Okay, the next question, David Mackinson.
Hello, can you hear me?
Yes.
Okay, well, thank you for a very, very interesting talk. And I was particularly struck by your contrast between mathematical completeness and cognitive completeness in a diagram. And looking at your example, it seemed to me that in that example, at least, the cognitive completeness could also be thought as a kind of mathematical completeness, but with respect to a richer structure. That is to say, in that example, you're looking at the partitions of this set into two, which is in some sense respects the dominant, the natural ordering relation over the set.
Yes, yeah, so you are responding to this graphic, right?
Yes.
Yeah, so yeah, so you're saying look at this as just a linear structure, maybe on a graph theoretic level, and then look at the partitions of those that are constrained by the fact that they need to partition sort of, yeah, I can. Yeah, no, that's really kind
Actually,
of.
there's a bit more structure needed because you don't want the partition, say, at the number 5 or omega plus 1, something like that.
Yeah. Yeah, so what I'm hearing you say is you can mathematically describe how this has been constrained to reduce the complexity quite simply. Yeah, great point. Thank you.
Okay, next question, Paul Healy.
Yes, thank you for the talk, Roland. It made me immediately think of Pythagoreans, and I hadn't thought of that before with other more mathematical squares like yourself, because like Moretti's ones that I spoke to him a long time ago about. And I think that it's possible to come at it from a different direction as well. My interest in the modal terms of inference. And I think Aristotle, as he comes down from Plato, is possibly more concerned with trying to get the sort of language side of logic to fit with the calculus. So it's coming at it from a different angle. So I'm not saying yours isn't the right angle, but I find that there's, you could represent different Pythagorean theorems using very similar sort of algebra. And I just wondered if you had any thoughts on that. Yeah.
What do you mean by Pythagorean theorem?
Well, the sort of the square of the hypotenuse is equal to the, the sum of the two adjacent squares, the opposite square and the adjacent square. There's quite a few visual representations of that theorem. And so you could say that they're like they're direct presentations of a mathematical relation.
Yeah.
But maybe when you're dealing with Aristotle, you're sort of more like trying to work out how inferences relate to impossibility and how that connects with the maths and the calculus. Yeah.
Yeah, it's absolutely correct that the first logical squares of this type were about logic and inferences and sort of a philosophy of language thing. And it's a little bit of a provocation to that tradition, because I sort of take it a little bit away from there and put it in a combinatorial foundation. But that's not to, in classical logic, the relation between Boolean algebras and fragments of first order languages or of propositional calculus, that's extremely well understood. So it's not an alien way of thinking if you take a somewhat more structuralist look at classical logic, for example. For me, the adventure of this paper was just to understand why these diagrams were so beautiful or elegant in being able to represent all these different features. But if you look at Alessio Moretti's thesis and some other publications, you can find images of this Tetrakis hexahedron, and it has been, he has labeled the vertices, for example, with modal logic, and you can see in one glance all the logical relations between 14 terms of a modal logic or a fragment of modal logic. So that's definitely within the purview of how this ought to be applied. It's just that in my exercise, I needed to find the canonical labeling, and I ended up with the set theory stuff.
Okay, thank you. Thanks.
Thanks.
Yeah, thanks.
Okay, the next question, Julius Stern.
Yeah, I type my question or wish for a tool of making nice diagrams according to your aesthetical and logical considerations. I think for all of us in this community, that would be an extremely useful tool. That's always in the background of our work, but we keep using ticks or PB diagram or whatever to draw by hand or by, what I mean, those diagrams. That's a real pain in the neck. So how can we get there? I know it's not a trivial wish to fulfill, but how can we get there?
It's a great point, and I think it's a natural next step to take from here to sort of, because you can create some sort of entry scheme that makes sure that the user doesn't make any mistakes, and then it just generates those diagrams. And that would go a long way towards bootstrapping some of the visualization work that we're doing. It would have to be programmed. I'll say thanks for the encouragement. And I'm not going to make any hard promises today, but it's good to know that you would be happy to have a look at that if it was made to exist. Thank you.
Yeah, and if I can add, I know that the diagram community has some work done on rules of how to draw those things so that they don't clump or don't superpose to each other. They have done some preliminary work that can be used, I think.
Thank you very much.
The next question, Anka Pascu.
Yes, hello. Do you hear me?
Yes.
Yes, thank you. Hello. So I have a question about what is the cognitive completeness versus mathematical completeness. How do you apprehend cognitive completeness? Is a very great problem. when you see cognitive completeness and mathematical completeness? That is one of my questions. And the second is maybe related, this study can be related to the model of formal concept analysis, which is not exactly in the same context. The context is more rich than your context, when the entity, if I well understood, the entities A, B, C are completely independent, defined in the set theory, not at all. And we are in the axiomatic set theory, inherited from Zermelo, Frenkel, and Bernays, Gödel, and so on, isn't it?
Mm.
Okay.
Thank you. I heard you.
So first, that all about completeness.
Sure.
Cognitive.
Yes. So my remarks about cognitive completeness,
Yes.
I fully admit, is very sketchy. But what I found I like this example of this infinity, because that's the level of complexity that fits with this tetrakis hexahedron polytope. And I looked at some diagrams where you have that mapped onto there. And although, I put some work into understanding why it's beautiful in its sort of relation to a mathematically complete system, I'm not as amazed with the result from the point of view of making an elegant thinking tool for me to understand that little conceptual system. Yeah. And then I was just sort of doing some auto analysis, and I thought, well, which are the distinctions that stand out as more salient than others? And I only at this point offer this observation, and it's supported by linguistic data, that we tend to split these linear orders into two halves that extend out to the extremes. And those are the concepts that have the shortest lexicalizations in the language of mathematics, finite, infinite. Yeah? We don't lexicalize, for example, the concept X is an empty set, or it's uncountably infinite. We don't create a new word for that.
Yes,
and if we don't create a new word for it, then that's a sign that it's not cognitively as salient than some other distinctions. And of course, we have a limited cognitive budget when it comes to lexicalizations. So there must be other constraints. And this was just a stab in the dark at saying what kind of constraints we might have, so we can create these overviews for these relatively complex systems, if you were to look at them from the point of view of combinatorial complexity, and still find a roadmap that feels complete in terms of how we understand it. But I do not have a theory of cognitive completeness that this is embedded in. This is just an observation that's a starting point, So I don't have more than what I offered here, but I do think it's a good observation.
Yes, I understand your point of view, but my question is, it's open maybe, if between mathematical completeness, mathematics is an abstract construction and the linguistic, in the sense of common language cognition, which is the link, the relation between, there are something in mathematics which cannot be expressed in common language and not to be explained, for how we explain the infinity for a child, for example, that is a progressive construction in the human mind and the relation is, can we pick up or not? I don't know. That is, thank you very much. Thank you.
I didn't even get to your second question, but I think the first one is more interesting, but it's also a very large question. I am in favor of not looking at language and cognition through the lens of mathematics all the time. You know, I think I look at the human organism as evolved under certain pressures, and we are just much better at certain cognitive tasks than others. And it's very expensive from a cognitive point of view to make two fine distinctions, right? So these things come into play, but if you look at mathematics, it's all about exhaustiveness and about systematicity, and those are not as valued in our sort of everyday cognition. So they sort of complete each other in ways that is extremely complex. So that's sort of my view in a couple of sentences. And that's also why I didn't really, I just said, well, those are sort of different goals. You know, if you want to display something that's mathematically complete, you have certain success criteria. But if you think of it from a more cognitive point of view, you might make a selection, but under certain constraints that are not mathematical per se. But that might be, as David Mackinson pointed out, that might, you might still characterize them formally.
Yes,
thanks. Yeah, I wish we could have a dinner and then talk more. I mean, yeah.
Maybe
Anyway.
it's a philosophy of mathematics and philosophy of language. A problem is not strictly in the mathematical construction, the system, the mathematics as a system, and maybe the relation between intuition and procedural thinking.
Right.
Maybe, I don't know. Thank you.
Thank you too. Thanks, and nice to make your acquaintance here.
David Mackinson has a new question.
Thank you for the opportunity to ask a second question, and I'll be very brief. None of your diagrams were trees, and that interested me because trees are very useful graphic devices. So I was wondering why. Is it you don't find them interesting or difficult to deal with or difficult to say anything interesting about them? I wonder.
No, I don't have an opinion for or against them. Just in this context, I didn't see an application of them. Do you see an application? Did I miss something that could be spelled out in terms of trees?
No, it's just that they are commonly used diagrams, used in logic and in combinatorics and in other places. So I was just wondering, that's all.
There was a question on the chat by Jerry Chandler. Maybe you can
right.
relate this.
Sure.
Jerry
he writes,
yes.
I do not understand why logical diagrams are not spatial. What is the meaning of visualization in this usage?
Yes.
So that refers back to some remarks that I made early on in the talk, I think. And of course, a diagram, well, the way I'd like to use these words is like this, is a two-dimensional geometric shape or a three-dimensional geometric object. Those are spatial, things. We can think of those, or we can, we can make objects that are approximations of them. Yeah. On the other hand, words, expressions of languages, formulas of formal systems, they all stand in relations to each other. For example, in classical propositional logic, you would have A and non-A, and those stand in the relation to each other of being each other's negations, a little bit sloppily put. So that's a relation, but that doesn't have, that's not spatial, because those are two, those are two propositions or formulas of a language. So that's not a spatial issue. A geometric shape is spatial, and a diagram is sort of in the middle, because a diagram uses geometric shapes together with some labels to visualize the non-spatial information or structure. So that was a point I was raising in the beginning. And what I'm also trying to say is keep those two domains separate and reflect on whether the visualization, the diagram that you've created, serves the purpose of helping someone to understand the somewhat abstract and non-spatial logical or mathematical structure that you're depicting or representing with the diagram. Think about statistical information, statistical data. 20% of all Germans have this and this habit. Well, that's not a spatial thing. That's just that's a percentage. If you're going to map that on a graph, you are going to come up with spatial, two-dimensional, something that you can print in a newspaper. That's data visualization. The data was not spatial, and you turn it into a spatial thing that's apt or adequate for human beings to read, because they've learned to read it. So that's a visualization task. And this is sort of the framework that I was trying to promote early on. So I think those remarks were in that question. I think, I've done what I can to.
Can I respond to that?
Absolutely.
Yes. I understand after listening to your talk, which I thought was very excellent in the terms of its clarity and its precision of language. And so that I appreciate that. And it did fill in some holes in my own thinking about the relationship between mathematics and logic. But the foundation for my question comes actually from the natural sciences. And particularly it comes from the observations of Louis Pasteur in 1860s with regard to the notion of crystal forms and left and right-handed crystal forms. You gave an example of a geometric object in your talk, which is very nice, and related that to crystal theory in its own way. But the point is that in chemical language, the language and logic of chemistry that uses the atomic numbers, then you necessarily require spatial visualization of abstract objects. So the spatial visualization of completely abstract objects, that is atomic numbers and compositions of atomic numbers, require a spatial visualization. And so that was the foundation of my question, but it also enters into the notions of the question with regard to trees and graph theory. If you look at this from a graph theoretic perspective, you have to think of categories and the use of the tetrahedron as one form of a category, one form of representation of a category. And that has a different set of relations than, or that extends the set of relations that you used in your explanation of your diagrams. So that's the basis of my question. I thank you very much for a very nice talk.
Thank you. That's really nice to hear, the compliment you made. So there are many links to category theoretic treatments of sets in my talk that I didn't state. I can tell you one of them. In my, you recall, I showed this analogy between three fundamental combinatorial concepts and then these geometric features of these polytopes. Let me find that real quick. Yeah. So I'm talking about this one, yeah. And these three concepts, you can spell them out in category theory if you look at the category of sets, as you know. So this would be in relation to monic arrows, and this would be in relation to epic arrows. And those are strictly dual from a category theoretic point of view. And permutations are isomorphisms. You can spell them out in terms of isomorphisms. And of course, isomorphisms are both epic and monic. So that little set of three concepts is tied together quite tightly mathematically. There are some other related or adjacent concepts that actually you can start to look for in these shapes, but it just becomes a little bit like a treasure hunt. And I didn't really want to take my audience there today, but yeah, so I appreciate that the point that there's a strong connection to categories. Not entirely sure the way I've just added something here is what you had in mind, but is that the case, or was that what you were getting at?
In part, yes, but in other parts, there still is unanswered questions. And particularly these unanswered questions is regard to the relationship between the atomic numbers and the geometric forms of chemical molecules. So that part of it does depend on permutation groups, but these permutation groups are of a very special form because of the structure of the atom as having both positive and negative numbers, as well as two different types of matter. And so you need a further opposition in terms of type theory to present if you would, the visualization of the structures, of the mathematical structures.
Yeah.
Such as DNA or other large molecules.
Yeah, I'm personally simply not familiar enough to make any sort of convincing link between what I've presented today and what you've raised. It does appear to me that these relations between formulas in a language, they are non-spatial even more so than the examples you've come up with, because obviously in the natural sciences, you're still talking about matter that exists out there in one way or form. I don't really understand the makeup of molecules, so I can't really comment on that. But I do think that in linguistics, if you look at a lexical field, a bunch of lexical items or concepts that are related, there's simply nothing spatial about that to begin with, that you are representing those spatial relations in a diagram. The diagram just serves a purpose of understanding the non-spatial relations. And it can do so better or worse. But that might be completely different in the cases that you've named. And there are many examples of diagrams in physics, like Feynman diagrams, I hear, where they play a really important role in how we conceive of that, and they allow us sort of mental shortcuts. And there's a lot more going on there that I didn't broach today, and I'd be uncomfortable going into in more detail. But I'll take that as a prompt to look into that a little bit more, because there must be more connections.
Okay, maybe a short question because we have exceeded time by Giulio.
It's just a follow-up.
Yes.
Just a follow-up on the question on trees. Trees are very useful to express logical relations in cladistic. That's the classification of species, genera, etc. And by the way, there are very good software to draw dendrograms. That's how biologists call those tree diagrams. So that may be of interest.
Thanks.
How is called the software? How the software is called?
Excuse me, what did you ask?
What's the software you mentioned? How is called?
I don't know by name. I have to check with my biologist friends and I give you the specific software.
Okay.
Yeah, I found
Roland?
something.
Yes.
Yeah, thanks for that. I'm going to look into it. Just Googled it and this came up. Ioannis, do you have a question or?
No, I think we have to close. Maybe Zanif has to make some comment or some closure.
Well, thanks to everybody for this nice session today. So I just remember that the deadline for the next square is at the end of this month. So it's still possible to submit an abstract. Everybody is welcome. And the next session of the Logical Universalist webinar will be in June. So it will be posted on the page of the webinar soon. And I hope to see you next month. All right. Thanks. Bye-bye.
Okay, thank you, everybody.
Bye.
Thank you too.